So redox is actually a pretty interesting topic. Redox is in our lives every day. So I'm going to give you some examples just to give you something to think about. So here is an old-fashioned battery, similar to your Duracell or Energizer batteries. We looked at the galvanic cells, and they were set up in beakers and solutions, and you could create the electrochemical cell, but obviously those are not very convenient or practical to carry around to generate voltage to run your electronics. So batteries are the application of redox chemistry that allow us to harness that power in a more useful way. So batteries are actually typically a lot more complex than just simple half reactions. There's a lot more going on here to make the battery work. This particular battery runs on a zinc anode, and that's pretty standard, but then you see a lot more complicated cathode here. And if you looked up the potentials for this, you could get your voltages for your battery. All right. Your button batteries are often mercury batteries. So mercury is a hazardous substance, so that's why you have to be so careful with the mercury batteries, because one of the products is actually mercury. So you get your two half reactions and your overall reaction here. All right, this is a lead storage battery. This is a standard car battery, not your newer electric car batteries. It is also referred to as a lead acid storage battery. So our half reactions here involve lead and lead sulfate, and it has to happen under acidic conditions. So when you're balancing your redox reactions, remember sometimes you have to balance them in acidic conditions, and sometimes those acidic conditions are required to make the reaction be able to work. So these are two half reactions you could look up on your table of redox potentials, and I think you would actually get about 2 volts for this reaction, but the typical car battery is 12 volts. So what happens is you put 6 of these in series with one another to get your 12 volts. And so back in the old days, you could actually remove the cap from your battery, and sometimes your battery would be dried out and it would not work anymore because the electrolyte was not functioning. The salt bridges couldn't flow, ions couldn't flow, and one of the simple solutions is people just put some water in it to get everything wet to get it running. Of course, that was temporary because it wasn't exactly the electrolyte that was needed. But nowadays batteries are sealed because they do have battery acid in them, the sulfuric acid, and just some interesting facts. Lithium ion batteries. If I were trying to figure out a battery, I'd probably go to the opposite ends of the table and make it my goal to use those things in a battery. So lithium is at the bottom of the table, and lithium solid is actually very good at getting oxidized. So it's a strong reducing agent and has a lot of potential to get oxidized. And so we are using those results right now as we use our electronics, our cell phones, and our laptops. And so that technology has come a very, very long way. Now, at the other end of the table, we have fluorine and some of our gases, but those are not as safe to work with. Even lithium is somewhat dangerous, so there's a lot of precautions that go into it because it's very reactive. But fluorine is not something we really want to carry around these days. Fuel cells are also a great form of a battery, providing electrical energy or voltage. So this has a continuous source. So what makes something a fuel cell is the continuous supply of reactants. So the most common fuel cell uses hydrogen gas and oxygen gas. And you just, if you have a way to feed those into the battery, then you can continually produce a reaction. And one of the advantages is it produces water. So that's why there's so much talk about fuel cells, because it would reduce carbon emissions and things like that and be very little waste. However, when you put hydrogen and oxygen together, it can also explosively react to form water. So the logistics of harnessing that power in our everyday lives is a lot more challenging. Corrosion or rust is also a redox reaction. It's a little more complicated than just iron getting oxidized. It has to have water, it has to have oxygen, and some acidic conditions. And we have two oxidations of iron, so iron 2+ and iron 3+ are involved to form rust. One last example is cathodic protection of an iron storage tank. So iron does rust because it gets oxidized. But if you can actually use another metal that's more reactive, like this magnesium is very reactive, it can supply electrons to the iron storage tank to allow it to be prevented from oxidizing. So therefore it would not generate holes and leaks and things like that into the ground. But you will have to remember, or whoever has these iron storage tanks has to remember, that their magnesium rods or cathodic protection rods have to be replaced, because they will disintegrate as the electrons are used up and magnesium ion is produced. So that's just a few examples of redox in our everyday lives, but there are many, many more, and I encourage you to learn more about those or recognize them when you see them.